Hi, and welcome to the third video of my concrete sustainability series. If you haven't seen the previous two videos, my name is Nikola Tosic and I'm a teaching assistant and PhD student at the University of Belgrade's Faculty of Civil Engineering and a member of our faculty's concrete structures research team. In the last two videos, we looked at environmental problems posed by the production of concrete, natural resource depletion, CO2 emissions, and waste generation. We also presented possible solutions to these problems, recycling concrete waste to produce recycled concrete aggregates to use instead of natural ones, and using industrial byproducts such as fly ash for cement replacement in large percentages, generally above 30%. If you haven't seen the videos or just want to review them, you can find the links in the description. Today, finally, we'll move on to current research being done by our team. I'll go over the topics we're investigating, present briefly our main results, and analyze how they fit into the bigger picture of striving towards sustainable concrete production. I briefly presented our research team in the first video, but I'll go over it again in this one. As you can see, there are currently 5 of us. We're headed by 2 professors, and 3 of us are doing our PhDs. We are a young research team, but we love the work we're doing, and we hope to continue doing it, and hopefully we will witness the fulfillment of our vision of a sustainable society which rationally uses scarce resources. Our work is multi-layered and multidisciplinary. We are of course interested in the global picture of concrete sustainability, but at the same time we are structural engineers, and so we are interested in concrete structures, their design and behavior. That's why we always try to implement the new green concretes in structural applications. First, from a more global perspective, we are trying to analyze and quantify the environmental, economic and social benefits of using green alternatives to traditional concrete. To assess the environmental impact of different concretes, we use the life cycle assessment methodology, or LCA, which, as I mentioned in the first video, is a methodology for evaluating the environmental load of processes and products during their life cycle. It quantifies and compares the emissions to air, ground and water arising during the life cycle of different concretes. In LCA, you can take different approaches and take into account different parts of the life cycle, such as the so-called cradle-to-grave, cradle-to-gate, or gate-to-gate scenarios. On your screens, you can see a possible cradle-to-gate scenario for concrete production, and the process is taken into consideration. We always try to gather data for specific conditions in Serbia for each of them. In the end, the emissions are compiled into several so-called impact categories. One of the most important ones is the global warming potential, expressed in grams of CO2 equivalent, which is a compound metric of CO2 and other greenhouse gases. This impact category can also be related to damages to human health, for example, expressed in disability-adjusted life years, a World Health Organization metric which signifies how many years of healthy life have been lost. Other categories include water acidification and eutrophication, photochemical ozone creation, and many others. On your screens you can also see a comparison of impact category values for several green concretes given as a percentage of traditional concrete. For example, we can analyze specific scenarios for concrete production in Serbia, taking into account realistic transport distances for cement and aggregates. Such analysis can tell us interesting things. For example, since river aggregates are mostly transported by freight barges and recycled concrete aggregates by trucks, per kilometer of transport, recycled concrete aggregates are a greater environmental burden. Only when their transport distance drops relative to that of natural aggregates, recycled aggregate concrete will be more environmentally friendly. Economically, we can analyze the prices of these concretes and see that because of the low price of river aggregates in Serbia, it can be difficult to make recycled aggregate concrete attractive to concrete producers. So we suggest some policy measures to stimulate its production and use. These can include increasing waste landfilling taxes, imposing taxes or restrictions on natural aggregate extraction, and subsidizing the recycling industry with income from those taxes. Finally, we can use a multi-criteria approach and sort of bundle together environmental and economic categories, weighting them according to stakeholder preferences, and analyze the results. This way we can easily see that when looking at the whole picture, recycled aggregate concrete is the optimal alternative for concrete production. Since these analyses justify the use of both recycled concrete aggregates and fly ash in structural concrete, the next logical step is to experimentally test the behavior of such concretes. This first requires the mastering of mixture design of such concretes. It's important to consider everything specific about them. So, for example, the increased water absorption of recycled concrete aggregates requires adding additional water into the mix to maintain workability. In the case of high-volume fly ash concretes, we investigated many cement replacement ratios, even replacing a part of natural sand in concrete so that we can use as much fly ash as possible. Beside usual properties testing, such as compressive and tensile strength and the modulus of elasticity, we are also testing the durability of these concretes. Carbonation resistance, electrical conductivity, freeze and thaw resistance, as well as chloride permeability are all important factors that define the service life of a concrete. If it's low and the structure deteriorates too quickly, the use of green materials will not be sufficient to make it sustainable. A relatively new and very interesting topic is the so-called carbonation modification of recycled concrete aggregates. What this actually means is that recycled concrete aggregates can act as a carbon sink in trapping CO2 from the atmosphere. This is because during the hardening of cement, one of the main chemical compounds generated is calcium hydroxide. It's responsible for the alkalinity of concrete, which helps to protect reinforcement from corrosion. In contact with air, calcium hydroxide in concrete reacts with CO2, creating calcium carbonate. While this is bad for existing structures because it lowers the pH value of concrete, it's actually very useful in the case of recycled concrete aggregates. Because crushed concrete has a large surface area, it can absorb significantly more CO2, partly annulling the emissions from concrete production. So far, accelerated carbonation tests have shown this can in fact improve recycled concrete aggregate properties by reducing porosity and lowering water absorption. Last but not least, we are testing the behavior of structural reinforced concrete elements made from both recycled aggregate concrete and high-volume fly ash concrete. The tests of material properties are only useful to a certain point, beyond which experimental verification of structural behavior is the only reliable source of knowledge. That's why so far we've tested both short-term and long-term behavior of reinforced concrete beams made from these concretes. We carried out tests to determine the ultimate flexural and shear strength of recycled aggregate concrete and high-volume fly ash concrete beams, and compared them with traditional concrete. The results are encouraging, showing that the low deflection behavior of these beams is sufficiently similar to the behavior of traditional concrete beams so that it can be considered to be the same for design purposes. On your screens you will see some photos of flexural and shear failures. We also use a digital image correlation to track the crack development in the beams. The special characteristic of concrete are its long-term properties, creep and shrinkage. Concrete creep manifests itself as an increase in the deformation of concrete in time under a constant load, and shrinkage as the decrease of the volume of concrete in time. Both of these phenomena can cause problems to concrete structures, excessive cracking and deflections, and the loss of pre-stress in pre-stressed concrete. That's why an experimental program is underway at our faculty to compare the long-term behavior of recycled aggregate concrete and high-volume fly ash concrete beams with traditional concrete beams and assess this critical aspect of their behavior. All of our experiments are just a tiny fraction of the research being done globally to investigate sustainable alternatives to traditional concrete, but it is our attempt to contribute to this field. Many more experiments and studies await us in the future, and hopefully more and more researchers and people in general will join in this endeavor. This was just a brief overview of our activities. You can find out more if you follow the links in the description, including full journal and conference articles on my ResearchGate page. I hope you've enjoyed these videos as much as I've enjoyed making them. If you have any questions, please post them in the comments or write me an email. I'll be more than happy to continue the conversation. Until next time, goodbye.